three normal distributions. Let's take a look at the histogram for the percent of foreign-born residents again. If we sort of look at the overall shape, we could consider sort of smoothing it out with a curve like so. That sort of defines the overall distribution. Consider Major League Baseball salaries. Again, if we smooth out the histogram, we see that it's heavily skewed, much more so than the percent of foreign-born residents, and we get a rough idea of the shape of the distribution with the smooth curve. Another example, suppose we have the body mass of individuals and a histogram here. We can smooth it out, and we see that this is a bimodal distribution. Lastly, if we look at a histogram of scores on an easy test, we see that it's skewed to the left because most of the grades, the scores are in the high range. And once again, we can kind of smooth it out. This is the beginning of what we'll discover in Chapter 3 about having to do with density curves, and in particular, normal distributions, which are widely used in statistics. We'll discuss the 68, 99, 95, 99.7 rule, the standard normal distribution, finding normal proportions using the standard normal table, and finding a value when given a proportion. In the first two chapters, we developed a kit of graphical and numerical tools for describing distributions. Now we'll add one more step to the strategy. So, when exploring quantitative data, we plot the data, make a graph. Look for the overall pattern, the shape, the center, and the spread, and look for striking departures such as outliers. We also calculate a numerical summary to briefly describe the center and the spread. Now, sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. For example, here is a histogram of vocabulary scores of 947 7th graders. If we draw a smooth curve over the histogram, this is a mathematical model for the distribution. To begin with, let's talk about the shaded area of the bars in the histogram. In this case, the blue shade, represent the proportion of scores in the observed data that are less than or equal to 6. This proportion equals 0.3, roughly. Now, if we look at the same proportion under the smooth curve to the left of 6.0, this proportion is equal to 0.293. Notice, very similar to the histogram. Now, if we readjust the scale, notice the scale on the bottom goes from 2, 4, 6, 8, etc. If we readjust it so that the area under the curve is exactly 1, then the curve is called a density curve. A density curve is a curve that is always on or above the horizontal axis, has an area of exactly 1 underneath it. A density curve describes the overall pattern of a distribution. The area under the curve is the proportion of all observations that fall in that range. The mean and standard deviation of the distribution, represented by the density curve, are denoted by Greek letter mu and Greek letter sigma, lowercase sigma, respectively. Now, our measures of center and spread apply to density curves as well as to actual sets of observations. The median of a density curve is the point of equal areas. That's the point that divides the area under the curve exactly in half. The mean of a density curve is the balance point, at which the curve would balance if made of a solid material. The median and the mean are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. Sort of illustrated here. Symmetric curve, right in the middle, and for an asymmetric, for a skewed curve, the long tail pulls the mean toward the right. Now, one particular important class of density curves are called the normal curves, which describe normal distributions. All normal curves are symmetric, single-peaked, and bell-shaped. A specific normal curve is described by giving its mean, mu, and standard deviation, sigma. Note, there are very many variables which can be approximated using a normal distribution, such as heights of people, weights, very many biological variables follow a normal distribution. In addition, the normal distribution is useful for other parts of statistics that we'll talk about later. So a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by its mean and standard deviation. The mean of a normal distribution is the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. This is sometimes abbreviated this way, with n, capital N, mu sigma. You'll see that in the textbook. I won't use it a whole lot. Now, for any normal distribution with mean, mu, and standard deviation sigma, approximately 68% of all the observations will fall within one standard deviation of the mean. Approximately 95% of all the observations fall within two standard deviations of the mean. Approximately 99.7%, virtually all of the observations, fall within three standard deviations of the mean. So we get something that looks like this. If the middle between -1 and +1 standard deviation makes up 68% of the data, between -2 and +2 standard deviations makes up 95% of the data, and between -3 and +3 makes up almost all, 99.7% of all the value. An example. The distribution of Iowa Test of Basic Skills vocabulary scores for 7th grade students in Gary, Indiana is close to normal, with mean 6.84 and standard deviation 1.55. First, we'll sketch the normal density curve for this distribution. They all look pretty much alike. What distinguishes one from another is the mean and the standard deviation. So here the mean, 6.84, is right in the middle, and the horizontal axis is ticked off in increments of 1.55, the standard deviation. So, what percent of vocabulary scores are less than 3.74? Well, if we take a look here, about 95% of the scores are within two standard deviations of the mean. That's 2 times 1.55 on either side of the mean. So what's left over is 5%, and that's split equally between the two tails. So below 3.74 represents about 2.5% of all the scores. What percent of the scores are between 5.29 and 9.94? Well, we know that about 68% of the scores are between -1 and +1 standard deviations of the mean. Note, because it's symmetric, that means that half of that, or 34% roughly, is between the mean and 8.39 or the mean and 5.29. 95% of the scores are between -2 and +2 standard deviations. So again, because it's symmetric, that means that half the scores are between 6.84 and 9.94. So we can use that to calculate this. About 34% of the scores are between 5.29 and 6.84, and about half of 95, or 47.5% of the scores, are between 6.84 and 9.94. So we just add those. So the percent of scores between 5.29 and 9.94 is about 81.5%. All normal distributions are the same if we measure in units of size standard deviation from the mean, mu, as the center. The standard normal distribution is a particular normal distribution. It has a mean of 0, and we measure it in terms of standard deviations of 1. If a normal variable x has any normal distribution with mean, mu, and standard deviation, sigma, then a standardized variable, z, equals an observation minus the mean divided by the standard deviation. That's called a standardized score. Because all normal distributions are the same when we standardize, we can find areas under any normal curve from a single table. That's the advantage. So let's take a look. This is Table A in the back of the book. There are many tables that are probably available on the internet. It is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z. So in other words, from negative infinity up to whatever the z value is. The table always gives that value. The z-scores on the table are listed along the top and down the side. And the areas are given in the body of the table. So let's do an example. Suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.83. So we use Table A. First, locate the row for 0.8 in the table. And that's with the z-score. Then, along the top are the hundreds units. So we locate the column for 0.03. Where those two intersect is the value. So the area under the curve to the left of 0.83 is 0.7967. That's the proportion of data less than z equals 0.83. Suppose we want to find the proportion of observations from the standard normal distribution that are greater than minus 1.72. Once again, we locate the row for 1.7 and then locate the column for 0.02. Now, this gives the area under the curve up to the z-score. So 0.0427 represents from the left, infinity to the left, up to negative 1.72. We want the area beyond that. Since the area under the entire curve is exactly equal to 1, then we just simply subtract 0.0427 from 1. That equals 0.9573. That is the proportion greater than z equals minus 1.72. All right, let's find another one. Find the proportion of observations from the standard normal distribution that are between minus 1.25 and 0.81. So we start. First, the area to the left of z equals 0.81 is 0.7910. Hopefully you can find that in the table. The area to the left of z equals minus 1.25 is 0.1056. We want the area between those two values. So up to 0.81 is 0.79, up to minus 1.25 is 0.10, etc. So we just subtract the two. So 0.7910 minus 0.1056. So the area between those two values is 0.6854. Now we'll talk about solving problems using the normal distribution in terms of the four-step process. So we express the problem in terms of the observed variable x, whatever that might be. We draw a picture of the distribution and shade the area of interest under the curve. It's really important to do that to get a sense of the actual area that you're interested in, because the table only gives you one thing. from negative infinity up to a particular z-value. Then we perform some calculations, look up numbers. We begin by standardizing the value and then restate the problem in terms of a standard normal variable z using this formula. Incidentally, the z-score tells us how many standard deviations away from the mean a particular value is. And we use table A and the fact that the total area under the curve is 1 to find the required area under the standard normal curve. And then we write our conclusion. So, example, according to the Health and Nutrition Examination Study of 1976 to 1980, the heights of adult men aged 18 to 24 are approximately normally distributed with a mean of 70 and a standard deviation of 2.8. Incidentally, the units here are inches. So what proportion of men are under 75 inches tall? First, sketch the region we're interested in. That's to the left of 75. Here the mean is 70, the standard deviation is 2.8. We could mark off the horizontal axis in terms of 2.8, but we don't need to. Next, we calculate the z-score. That's the value we're interested in, 75, minus the mean, 70, divided by 2.8. So 1.78 is the z-score. That tells us that this particular value, 75, is 1.78 standard deviations above the mean. Then we find the area corresponding to a z-score of 1.7 in Table A. In this case, the area is 0.9625. So the proportion of men who are 75 inches tall or less is 0.9625. Okay, we'll use the same setup here and ask what proportion of men are over 66 inches tall. So first sketch the region we're interested in. 66 is less than 70, so the area we're interested in, the green area, is from 66 on. So again, we calculate the z-score. 66 minus 70 divided by 2.8. So that tells us that 66 is minus 1.43 standard deviations from the mean. The negative indicates that it's to the left of the mean. So now we find the corresponding area in the table. From the table, the area is 0.0764. Remember, that's up to a z-score of minus 1.43. We want greater than that, so we want the other side. So we subtract that value from 1. 1 minus 0.0764, 0.92. Now, suppose we're interested in knowing how tall a man must be in order to be in the lower 15% of men aged 18 to 24. So we're interested in finding, essentially, we know what the area is. So we know that a person is in this lower 15%. But we don't know what the corresponding z-score is. So we want to find that out. This is sort of an inverse problem. In Table A, we find the area that's closest to 0.15. So take a look at Table A and notice this value, 0.1492, is about the closest we get to 0.15. Keep in mind, that represents 15% of the data. Now we're interested in the z-score that's associated with that. So from the table we find the z-score is minus 1.04. So to find out how tall a man must be, we have a z-score of minus 1.04, a mean of 70, and a standard deviation of 2.8. So we need to unstandardize the z-score to find the actual value. So we take the the z-score formula and just plug in the numbers where appropriate. We're looking for the observed score x, so that's what we don't know. We fill in the rest of the numbers and then just kind of manipulate things around and solve for x. So we get x equals 67.09. So a man would have to be approximately 67.09 inches tall or less to place in the lower 15% of all men in the population. So to review, we defined and described density curves. We described normal distributions, a particular type of density curve. We described and applied the 68, 95, 99.7 rule, described the standard normal distribution, and we did a few problems performing normal calculations.